In this video, we're going to look at different factors that can both increase and decrease the size of a population of organisms. If we wanted to increase this population, the two simplest ways to do it are we could add organisms by having members of this population reproduce and give birth to new organisms, in which case we would measure the birth rate of this population. The other way is by taking organisms of the same species that live outside of this population and have them migrate in order to join this population, and when we measure this, we would be measuring the immigration rate. Now, to measure the rate at which a population decreases, we would simply look at the opposite, firstly by looking at the number of organisms that die because of old age or are killed by predators in order to find the death rate of our population, and secondly, look at the number of organisms that leave the population in search of better living conditions, in which case we would be looking at the emigration rate. And if we take the birth rate and add it to the immigration rate, and then subtract from that the death rate and the emigration rate, we would be able to find the overall rate at which this population is increasing or decreasing, and from that we would be able to see if the population is sustaining itself, if it's growing at an unsustainable rate, or if it is actually decreasing to the point where it is in danger of localized extinction. Now, we can represent population growth rates on a graph where we measure the population size against the passage of time. And if we take a look at this graph, which is mathematically what we call an exponential growth curve, let me just spell that correctly, we can see if we draw individual lines that kind of mirror the shape of this graph, we can see that the slope, the vertical change divided by the horizontal change, is increasing in this graph as we move forward in time, which means the population rate is actually growing at increasing rates, meaning that our population is actually growing at nearly an uncontrollable rate. Now, this almost never happens, and in fact, this type of growth curve is only observed under the most ideal conditions where the natural resources that organisms need are effectively infinite to allow all organisms to be able to survive. By natural resources, we can refer to the big three, that being food, water, and shelter, which allow them to survive, but we can also treat the number of reproductive partners, that being the number of organisms in the population with which they can reproduce and make the new generation. When all of these conditions are effectively unlimited is when we get exponential growth. However, as we'll see, this almost never occurs under natural conditions because a number of environmental factors limit population's ability to reproduce indefinitely. Now, the first of these factors are what we call population density dependent factors, and we say that they are density dependent because these factors have greater effects on a population when that population has a very high population density, meaning that not only do we have a large population of organisms, but we have a relatively large population of organisms within a relatively small geographic area, meaning that these organisms need to share their living space, their hunting ground, and their food and water supplies with each other. Now, for obvious reasons, the higher a population gets, the more limited the resources of that ecosystem are. And again, these are the big three. The more limited the food, water, and shelter of the ecosystem is in order to support a large population. The more organisms there are, the more they will have to compete with each other for the same resources within that ecosystem. And this also applies to reproductive partners, which we call mates, because now if the organisms want to reproduce, they don't just need to compete for food, water, and shelter, but also need to compete with each other for the ability to reproduce and have offspring. Now, aside from natural resources, there are two other factors that increase in terms of their severity in large populations grouped very closely together, the first of which being disease, and this actually makes perfect sense because the more organisms there are in very close quarters together, the more easily disease can spread from one organism to the next, to the next, to the next, resulting in the entire population being infected, whereas this is much harder to do in smaller populations spread over a larger geographic area. Large populations in a small geographic area also mean that it's much easier for predators to attack this population and kill members of the population for food. However, when it comes to environmental factors, many of them, especially those related to weather conditions, belong to a category that we call the population density independent factors. And when we say that these factors are independent of population density, that means that these factors, which again are mostly weather conditions, will stop population growth from getting to a certain point in all populations, regardless of the number of organisms that exist. For example, if we consider the rate of snowfall or rainfall, that being the rate of precipitation within an ecosystem, this is important for populations because it controls the amount of water that exists within a population or within an ecosystem, and the number of organisms within a population is not going to affect the amount of precipitation that falls. That happens regardless of the number of organisms present, and all organisms in a population, regardless of the number, will be affected by a drought equally. This also applies when we look at the temperature of an ecosystem, because not all organisms are adapted to survive in very dry conditions like a desert, nor are many organisms adapted to survive in very cold and snowy conditions such as in an ice desert or a permanent winter biome like a tundra. So the ability of a population to be adapted to a specific temperature condition has basically nothing to do with their population density. A small population that is poorly adapted to living in a desert will die just as easily as a large population will. Lastly, and probably most obviously, we have natural disasters. So the simplest way of putting this is it doesn't really matter how many organisms are within your population. All of them are going to die if a volcano suddenly erupts within an ecosystem. Likewise, for if a tornado swallows up the populations of an ecosystem, or the same damage due to hurricanes and earthquakes. How big the population and how well spread out they are within a geographic area is really of no consequence. They will all be pretty much equally negatively affected by horrible natural disasters such as earthquakes, volcanoes, hurricanes, or tornadoes. In the next video, we're going to look at how to represent population changes under non-ideal conditions where the exponential growth no longer holds true.